Okay, so let's look at time dilation. How does time change from one observer to another observer? Well, we have to find a means of measuring time. We have to define a clock and then compare what the two observers observe about this clock. Now, we know that light is something that doesn't change from observer to observer. You say, whatever clock you are using is more or less a pendulum. The mechanical clocks are just pendulums, basically. But we don't know how the behavior of pendulum changes from one reference frame to the other reference frame. So we cannot really use such a watch. Electronic devices are similarly. Well, there is a kind of an electronic pendulum inside. And we don't know, without knowing how that pendulum will be observed by different observers, we cannot really use it. But there is one thing that we already know that doesn't change from observer to observer, the speed of light. So that is why we need to use the speed of light to define a clock and then see how different observers will see the clock. So we basically imagine such a system. We have a light source, and then there is a mirror. And let's say they are separated by a distance L. And then we send some light ray. It goes up, and then the mirror reflects it back, and then it comes back. So if you just can measure, then you can measure how long it takes to go up and down. Or you can say that you can adjust this length L in such a way that the time it takes for the light ray to go up and down should be 1 second. You can define second in such a way. You say that, okay, 1 second will be the time it takes for the light ray to go up and down. That's also a valid description. How long it takes for the light ray to go up and down?
2L over 3 to the 3 times, not times the 8.
2L over 3, C. Let me just call this T0. You see here, the clock is at rest. Well, about one suggestion, whenever you are writing expressions, either write everything numerically or write everything symbolically. Don't write this as 2L divided by 3 times 10 to the power 8. So everything should be either numerical or symbolic. Don't mix them.
Why the measurement error in distances is not applicable in this?
Well, you see, I don't know what L is. If I want to give some numerical number to L, there is a measurement error over there. So, another question, is this the question you were asking?
Şey kastediyorum hocam, normal ölçüm hatası değil mi de? Az önce bahsettiğim delta X'in.
No, you see, here what I'm imagining it, I have put a light source over here at rest, and then a mirror over here again at rest. So it just goes up and down. So how much does the light beam move? That was what we had called delta X. But in this problem, delta X is it moves L up and then L down. The total distance covered is 2L. So time it takes is 2L divided by the speed of light. By the way, the C is equal to 3 times 10 to the power 8 meters per second is an approximate expression, but we know the speed of light exactly. The speed of light doesn't have any measurement errors. No, mu 0 and that not because of mu 0 and epsilon 0. Speed of light is defined to be, well, there should be a precise number over here. Not the most precise one. The speed of light is a quantity that we define, not something that we actually measure. In the sense that we define the meter in terms of the speed of light. We say that 1 meter is the distance light covers in 1 over whatever we had defined the speed of light to be in that much seconds. So if you want to measure some length, there will be an uncertainty over there, but not in the measurement, in the definition of the speed of light. It is a constant that we define, like the pi. Pi is a constant we define as the ratio of two different lengths.
How is light defined? How is C defined?
We define C to be 2.9997 blah blah.
Yeah, I mean,
That's the
defining
definition.
of the ratio of circumference to the diameter. Is there something like that?
Yeah. C is just a constant. Yeah, it's not like that in the sense that it's not the ratio of two things, but C is just defined to be that number times meters per second. Okay, now let's go back to this example. So this is our clock. In the rest frame, the light goes up and down. It takes it t0 seconds, or t0, whatever your unit is. Now let's consider another observer. Let's say that we have a spaceship which contains our clock. The spaceship is moving with a speed, let's say v. Now that definition was for an observer in the spaceship. Now we are an observer outside the spaceship, and the spaceship is moving with a speed v relative to this outside observer. So what will it see? Well, this beam, this mirror, and the light source, they will be moving with time. So at the next time, they will be over here. At the next time, it will be over here. Also, the ship will move, but I'm not plotting it. So initially, the light starts from here, but then it hits the upper mirror. So the light should be moving along this line relative to the outside observer. And then it just comes back. It's reflected by the mirror, and then again hits the lower surface. Let's assume that this whole thing took a time t. Within a time t, again observed by the outside observer, the light beam started from here, moved to the upper mirror, and then came back to the lower surface. So how can we determine this time t? Well, the horizontal distance, well, let me just somewhat do it like this. This distance is vt. What is the height? Are you sure? So, are you sure that there is no contraction in the vertical direction? What do you mean CT? This distance. Why should it be CT? At least for the observer in the spaceship, it's just L. Your friend claims that it is also L for the outside observer. But in the last hour, we already discussed that the length changes from observer to observer. So how do we know that this vertical length does not change? Okay, so how does it mean that the vertical, how do you know that the vertical distances do not change? Because? How do you know that? You're just repeating yourself. How do you know that the vertical distances do not change? Okay, so you are again repeating what your friend said, that in the vertical direction there is no contraction of length, there is no change in length.
There is no movement upwards. So
okay, again, all of you are stating the same thing. You are all saying that in the direction perpendicular to the motion, there is no length contraction. That is your claim, right? How do you know that?
Do we know that? I mean,
Yes,
are
we
sure
will.
of that?
We are sure of that. We will discuss it. Well, okay. Your comments. I mean, we will discuss it when we are discussing length contraction. Well, you see, reference frames cannot be same in one direction and different in the other direction. The reference frames are either the same or they are different.
There is no position change in
No, you have already made lots of comments. He didn't make any.
The time it takes for the ball to go up is the same as the time for it to come down.
Okay, that's another nice comment. So does it take the same time to go up and then the same time to go down? I would say yes. Because for the outside observer, that's the length. Oh, we are already making the assumption that it's the same. Okay, we will be making two assumptions here, basically.
We can say that since the two mirrors are in the same frame of reference relative to us, we are observing from outside, but the two mirrors are both inside the spaceship, thus they are moving in the same direction. Any change in upper mirror will be cancelled out by bottom mirror, I guess.
What does it mean to be cancelled by?
Since they are not moving relative to each other.
Okay.
They should
But you see, even if you had a rod horizontally, different points on the rod are not moving relative to each other. So your argument should also hold for them. They are also in the same reference frame. They are at rest in the same reference frame. C is constant. That's also already one of the postulates of special theory of relativity. For every observer, C is constant, which is also verified experimentally by the Michelson-Morley experiment.
If you can observe the spaceship, then if it's not contracting, the mirror is also not contracting. If you can observe the spaceship outside, it's not contracting, then the mirror will also not be contracting.
Why not?
Because if you can observe it, then light will contract.
Well, what do you mean? Why does it contract if it's horizontal? So why doesn't it contract in the vertical axis but in the horizontal axis? Okay, I will just pass this. For the time being, okay, you didn't make any comment.
We set up the distances before starting the experiment.
True. But we set up to be L for an observer in the ship. So we are not changing it anymore. We are looking at exactly the same mirrors. There is the observer in the ship looking at these two things, and there is the observer outside looking at exactly the same thing. Okay, I will just, for the time being, state that we are assuming the length to be the same, L to be the same. Okay.
Can we say that in the first experiment, since the mirror setup is not moving relative to us, we can make the assumption that when something is not moving relative to us, length doesn't change. In that case, if light didn't reflect back where it's supposed to be, we could say that the velocity does change the length in some other direction. We can make that assumption from that first setup, I guess.
Well, you see, I can make the same argument if those two objects were placed along the direction of the velocity. If let's say the setup is moving like this, your argument, if it were true, it should hold for this arrangement and also for this arrangement. Right? I don't see any difference.
No, I was not trying to say that.
Mm-hmm.
I was trying to say that if that mirror setup is not moving initially, when
okay.
we do the first experiment,
no, you see, okay,
we can observe a time dilation with that.
Okay, so let me also emphasize one more point. I'm not talking about two different observations. That is one thing you have to always keep in mind. The second thing is I'm always looking at inertial reference frames. So my reference frames are not accelerating. So my objects are always moving at constant speeds. I just compare two different reference frames or two different observers. In a sense, there is an observer here, there is an observer over here. The observer inside the ship will see this thing. Well, at the same time, let me put some quotes there because this phrase also doesn't have any meaning. But at the same time, the outside observer will see this thing. So the inside observer and the outside observer are observing exactly the same events in different reference frames. So I'm not just changing the setup. Anyway, so I will just break this discussion for the time being. For the time being, I will just assume that L is the same. Now, after we discuss time dilation, we will also discuss length contraction, and then we will prove that vertical directions do not change, vertical length. Okay, there was another comment. How do we know that this time and this time is exactly the same?
Because it's in the same reference frame.
Well, what we are actually assuming is that the mirrors, the angle of incidence is the same thing as the angle of reflection. I will stick with that. Well, is that an assumption? Does it hold in every reference frames? Well, challenging that, with that assumption, what we observe, the consequences of those assumptions turns out to be correct. So basically, I'm assuming that these two angles are also the same. If those two angles are the same, this length and this length are exactly the same. By the way, this length is not Vt, it's Vt over 2. So the whole distance whole time is t. Half of it is over here, half of it is over there. Vt over 2, Vt over 2. Well, the rest is just Pythagorean theorem. So what do we know? Vt over 2 squared plus L squared, this length plus this length squared plus this length squared should be equal to this length squared. What is this length? Why Vt0 over 2? Vt0 over 2 is L. L is this length. You see, L is, no, sorry, not Vt0 over 2. So you are saying that if V is 0, this length is also 0. So that's what, if you say that this length is Vt0 over 2, then that would be the consequence. So if V is 0, that length would be 0. Which, Well, we have the speed of light. The speed of light, the light is moving from this to that point with the speed c, and for a time t over 2. Well, in a couple of lectures, I will also say that c is not the speed of light. But for the time being, let's just say that it's the speed of light. Well, let's just solve for t. L squared is a t squared over 4, c squared minus v squared, which tells me that t squared is 2L squared over c squared minus v squared, or t squared should be equal to 2L over c, or let me say t is equal to 2L over c divided by 1 minus v squared over c squared, which is 2L over c was just t0.
Time değişimi bunun yine velocity v grubunda farklı bir yönde hareket. Hani yatay olarak değil de 45 derece ölçüm etkilenir miydi?
So what you are saying, is this your question? Let's assume that the spaceship doesn't move in this direction, but the spaceship moves in that direction. So we will have a different expression for t. We will have a different expression for time dilation. No. The L will change, everything will change, it becomes a much more complicated problem, but this expression will be exactly the same.
Could you please clarify the T and T0?
Which one?
T and T0, what's T and T0?
Okay, you see, we have this setup. we have the light source, another plane, reflecting plane, and the light source sends a beam up, which is reflected from the plane and then comes back. So you, for example, let's say you are in the plane, in the spaceship, you look at your time, and you arrange L such that the time for the light ray to go up and down is just 1 second. So you can just count your seconds. Okay? So you count, let's say, 5 seconds. It goes up and down. And then there's the outside observer. What the outside observer, this is what you will see. The beam just moves up and down, up and down. So you conclude that in 5 seconds, you just lived 5 seconds. Okay? Now there's the outside observer. He looks at you. What he will see is that the light ray will go up and down. It will just make all this zigzag. So let's say after making 5 zigzags, he will look at his watch. Depending on your speed, he will see that 6 seconds has passed, not 5 seconds. T0 is 5. In this example, T0 is 5. But T is 6. So it made 5 zigzags, but in 6 seconds. Okay, related to your question, by the way. So, okay, this is just one very simple watch. What about other watches? You see, does this tell me that the clock on the mechanical clock on my wrist, will it also be slowed? My heartbeat, will it slow? That's also another watch. Not so precise, but another watch. Or the aging speed, the speed with which I age. That's just another clock. I can, in principle, use it to measure time. So will they all be affected? Again, the answer is yes, but why? How do we know that? No. The answer is simpler.
Synchronous? They are synchronous.
Why? How do you know that they are synchronous? Maybe speed affects my mechanical watch differently than this watch made with light. And it will affect differently my heartbeat.
They are dependent on time.
Which time? Now we are saying that time is relative. We started to define time for every reference frame. Why not take one more step further and define time for different processes? You see, the laws of physics should be the same in every reference frame. Well, maybe just a corollary to this one is that if you are in a closed container, closed room without any means of looking outside, if you are in an inertial reference frame, there shouldn't be any means of you telling whether you are moving relative to something else or not. There is nothing that can tell you that you are moving or not. If, for example, it happened that the time measured by this light clock would be different than the time measured by my wristwatch, then I can tell that I'm moving. It shouldn't be. It's not allowed. It can never be. So all the times should behave exactly the same way. Also for your example, when you said that what happens if the spaceship doesn't move vertically, but in some arbitrary direction. Well, that's another watch. But that watch should also behave exactly the same. And that is basically the proof why whatever watch you have, the time measured by the watch in its reference frame will be different than the time measured by an observer for an outside observer. And if they are moving with a relative speed v.
Hocam bu faktörü daha doğrusu yani en azından bu formülü türetmenin asıl yolu bu mu? Yani şu yüzden soruyorum. Biz 109 dersinin başındayken sadece örnek olarak şey anlatmıştı. Kara deliklerin yarı çapını ölçmek için için bir formül türetmişti. Bunda escape velocity'yi kullanarak yapmıştı. Ama bunun asıl türetiminin bu olmadığını söylemişti. Yani bu şekilde yapmanın çok doğru olmadığını söylemişti.
Well, you see, for example, you can drive the radius of a black hole using Newton's dynamics. You miss a factor 2. That's one problem. Because basically you are using Newton's dynamics. Here, what are we using to obtain these derivations? We know that Newton's gravitational law is not precise, is not really correct for black holes, but it somehow gives the correct answer. What are we using over here, which might fail? Well, okay, so here in this expression, we are using basic kinematics. Here, again, we are using basic kinematics. And also we are using Pythagorean theorem. Is this true? No. Not all the time. This is true in what we call in flat spaces, that is true. If the space is not flat, it's not true anymore. So that is the assumption we have. But what do we mean by flat space? Means basically that we are restricting ourselves to special theory of relativity. So within special theory of relativity, this is correct. What do I mean by flat space? Let's just imagine a sphere. I can draw a triangle over there. You see here, this is a line as straight as it can be on that surface. This is another line that can be as straight as possible on that surface. And this is another line, which is again okay, that's not straight, but as straight as possible on that surface. This is 90 degrees, this is 90 degrees, this is 90 degrees. The sum of the angles of a triangle doesn't even add up to 180 if you have curved surfaces. That's what we mean by curved space. And general theory of relativity tells that space is curved, not flat. So Pythagorean theorem doesn't hold in as long as L and this Vt are infinitesimally small. If they are not infinitesimally small, this will not hold. Anyway, that is not within the context of this course, let's say. General theory of relativity is a whole different story. Any other questions on this time dilation? Imagine the apple. Okay, let's leave aside this curved space for the time being. We can discuss after the lecture. Or we can continue after the lecture. Any other questions on this time dilation? We are in a flat space. Pythagorean theorem holds. There's no gravity, etc. Okay. No, this is true all the time. For every observer. Even when you are moving with the bus, coming to school, and your friend is just on the sidewalk, just standing looking at the box. And this will still be true. But then why don't we observe it? You see, typically, what is the speed of a bus? Well, let's say depending on the driver, something around 100 kilometers per hour. So which is around 30 meters per second. I mean, I don't have to be precise to reach a conclusion that I want to reach. Well, let's look at that factor, 1 over 1 minus v squared over c squared. So let me calculate V over C here. V over C is 30 meters per second divided by 330 times 10 to the power 7 meters per second, which is 10 to the power minus 7. So let's just look at this factor, which is 1 minus 10 to the power minus 14 to the power minus 1/2. Well, 10 to the power minus 14 is very small. So I can use the binomial expansion. This is approximately 1 plus 1 over 2 times 10 to the power minus 14. What I used is 1 plus x to the power n is approximately 1 plus n times x, as long as x is much smaller than 1. So you see, the deviation in time, the difference in time measured by you in the bus and by your friend on the sidewalk is 1 part in 10 to the power 14. And, well, at least my watch is not precise enough to measure that. So when I said that Newton's mechanics is not really wrong, it's correct. Special theory of relativity tells us that Newton's dynamics is wrong, within certain limits. So these are the limits. If your equipment is not precise enough to measure some deviations of 1 part in 10 to the power 14, whether you use Newton's dynamics or special theory of relativity, you get exactly the same result. So this expression, is it valid only if speed is close to the speed of light? No, it's valid all the time. But if the speed is not very close to the speed of light, it is almost exactly what you get from Newton's dynamics, that time is absolute. T is equal to T0.
What if the observer also moves? Will we use the relative velocity instead of v?
Before that, let me ask another question. Yes, by definition, observer cannot move. No. You see, you are the observer. Are you moving?
I'm not moving at the moment, but I can move.
I am the observer. I'm making the observation, and my position is not changing relative to me. I'm not moving. You are all moving. So it's kind of by definition the observer cannot move.
So we will use the relative velocity in this case.
I don't know. I'm only using the velocity that I measure. Do you call that, if you want to call that relative velocity, fine. That's the velocity for me. Okay, let me ask another question, though. It will be related to that one. So if I'm moving, I'm not moving, you are moving. Let's say you are moving very close to the speed of light. I will look at you, and I will see that your time is passing slower than mine. But then you also look at me. What will you see? Will my time be running slower or faster than yours?
Faster than mine?
No. It is also slower than yours.
Okay. Because I'm the observer.
You are the observer. So when I'm making the observation, your time is slower. When you are making the observation, my time is slower. Well, everything is relative. We can only talk what an observer will see relative to himself. But that brings us to what's called the twin paradox. Well, it's not really a paradox, but it's called initially it was called the paradox, so that sticks. Well, the idea is this. There are twins on Earth. And one of the twins decides to take a spaceship. He takes a spaceship. And moves at a speed very close to the speed of light. And then he just goes to the next star. He moves towards the star and then comes back. So let's say I'm the twin on Earth. I look at my twin. His time is running slow. So 1 year passes according to my watch. When I look at his watch, just 1 minute has passed. Another year in my watch, I look at his watch, another minute has passed. So he goes and comes back. And in my watch, let's say 20 years has passed. In his watch, it's just 2 hours has passed. You agree? It might, we can arrange the distances and the speeds according such that this might happen. Do you agree with this description? Okay, so now let's see what the twin will see, twin in the ship. Well, we always said that the speed is relative. So he makes the observation that I am moving. He looks at his watch, 1 year has passed, and he looks at my watch, it's just 1 second has passed. No, 1 minute has passed. He again looks at his watch, another year has passed, and then looks at my watch, another minute has passed. Well, it doesn't really work with the numbers I give because according to his watch, if 20 minutes has passed, he will be back. But let's just skip that detail for the time being. And then he goes and comes back, let's say in a couple of years. And according to him, my watch has always moved slower. So I should be younger. According to me, I'm observing him. His watch has always moved slower. His watch on the wrist, plus his also biological watch, they should be synchronized. So he should be younger. But then we come to on Earth, we have a family union, and we shake hands. So which one of us will have the wrinkles? Either he will have the wrinkles or I will have the wrinkles. One of us will be old, the other one will be quite young. So this is the idea of the paradox. So which one? Yes, that's basically the answer. You see, we have derived this time dilation and all the previous discussions were based on inertial reference frames. We cannot use those results in non-inertial reference frames. So what happens is my frame has always been inertial. So I can use all those results in my frame. But his reference frame hasn't been inertial all the time. At least even if he just moves at constant speed for some time. And during that time, I can use the special theory of relativity, and he will look at me, and my watch is slower, etc. But when it reaches the destination, it should decelerate and accelerate backwards. So during that time, at least, he is not an inertial observer. So the results we have do not hold for him anymore. He should take into account the acceleration, which is the realm of general theory of relativity. And that tells me that what my twin will see is, let's just ignore the acceleration while he's taking the ship. Okay, he's in the ship. We are at the same age. From his perspective, he will look at me. He will see that my time is flowing slowly. My time will always be running slower until he starts decelerating. When he is accelerating, when he looks at my watch, the time in my reference frame will start to flow much faster. And when he slows down and then he speeds up, during all this time there's acceleration, so my watch will move faster. So although he thought that I was much younger than him, during this acceleration period, after this acceleration period, when he looks at me, he will see me much older than him. And after the acceleration stops, as he is moving with constant velocity, I will age slower, but I am so much older. When he reaches Earth back, I am still older than him. This is what general theory of relativity tells us.
Yavaşlama periyodu olmasa sadece giden bir gemi düşünüyorum. Hangisi önce ölür?
Well, you see, how do you know that Which one dies first? Okay, any questions on this twin paradox besides that one? You see, what happens is this result doesn't hold when one of the reference frames is not inertial. When the observer is a non-inertial reference frame. So this observer, when he's changing its speed over here, it's accelerating. It's a non-inertial reference frame. And what general theory of relativity tells us is that if there is such a non-inertial reference frame, it's such an accelerating reference frame, the time slows down for my twin. So his time slows down. So although up to this point, according to him, my time has slowed down, during this acceleration period, he will see that my time has accelerated. My time is running much faster. So I get old, also according to him. Well, the same thing. If the acceleration is over, if he is moving at constant speed during the rest of his trip back, then he will see that I am aging slower. But you see, I'm aging slower. During a period, I'm aging much faster, and then again, I'm aging slower. How much did I age? Well, you have to sum all of them up. Have you watched Interstellar? You should watch it. Okay, I don't want to go into that because that is, as I said, general theory of relativity, which tells us that in regions of gravity, if there is gravity, time slows down. But general theory of relativity also says that gravity and acceleration, they are basically the same thing. Okay, any other questions? Okay, so your friend had a question. He said that, let's say that me and my twin, we both have, let's say, 20 years. After 20 years, we will both die. My twin takes this ship and starts moving at a fast speed. Who will die first?
How do we compare the events?
Question to you. How do you compare the two events? Or let me have a cheat. Give a cheat. So let me rephrase the question. Which twin will see the other twin die? Both of them. Assuming that if we were both living on Earth, none of us would take the ship, then we would see both of them die. We would each see the other one dying. So if we have this ship, one of the twins takes the ship, which one will see the other twin die? None of them. Time. Okay, I am on Earth. When 20 years passes according to my watch, according to his watch, depending on his speeds, for example, 10 years would have passed. So he will not die, but I will die. According to him, if 20 years has passed in his watch, just 10 years has passed in my watch. So he will die. I will not die. So none of the twins will see the other one die.
Isn't this question kind of break if we assume that even the infinitesimally small amount of acceleration causes unsynchronized clocks?
Okay. How much unsynchronized?
Even if the spaceship moves 1 meter per second relative to me for the whole distance, he needs to accelerate to 1 meter per second.
Okay.
This will change the clocks between them.
Okay. Well, sure. I mean, if you want to make this more precise, you have to put the acceleration in the initial trip, the acceleration slowing down, the speeding up, and slowing down. You have to put all those numbers into the computation.
I mean, he tried to say that they both have 20 years after he finished his acceleration and moves faster after constant speed. But when do they know they have 20 years? They won't know each of their 20 years started. Because of their...
No, I mean, we are just making a very simple assumption. I mean, I don't know when I will die. Nobody knows when they will die. We are just making a simple model. Or you can say, okay, rather than using death, let's say you have an alarm clock. And one alarm, and you both agree. So there is the spaceship, there is the guy on Earth. You both agree that the spaceship will pass just next to you. When you are side by side, you both agree to set the alarm to 20 minutes. And then there's no acceleration in this problem. The question still holds. Which alarm clock will go first? Well, in the reference frame of the Earth, for the observer on Earth, the alarm clock on Earth will go first. For the observer on the spaceship, the alarm clock on the spaceship will go first. Which, by the way, brings us to the question of simultaneity.
During this process of, the spaceship and this car, how does this information is transferred?
Yeah, you use some light, but you see, okay, there will be two factors to take into account. Let's say the light will also take some time to reach from here to here. You see, when the clock over here shows, let's say, 20 seconds has passed, and if the light takes 5 seconds to reach here, when you see the 20-second mark, the clock over here will show 25 seconds in your reference frame. Okay, so, but when we are saying time dilation, this one will happen first, this one will happen last, we are taking away all these effects. You see, the reason why we defined this reference frame, we have watches in this reference frame. Actually, what I do is, when the ship is, let's say, moving from here at this point and moving, I look at the watch on the wrist of the observer in the ship, and I look at the clock at that point in my reference frame, and I compare the two to eliminate the effects of the finite speed of light. So those effects are already taken out. This time dilation, this slowing down, is not just an apparent effect. It's an actual effect. For example, if you imagine thunderstorms, when there is a thunder, you first hear the lightning and then you hear the sound. It's not because the sound appeared after the lightning. They have different speeds, so if you just take those into account, etc., you know that they happened at the same time. Just like that, you when you observe something, okay, when I look at the stars, I can measure their age. I can say that, okay, let's say assume we have a star that is 1 million years old. If I want to talk about its age now in my reference frame, well, it's 1 million years old. I have to measure how much the light takes to reach my detector. If it's also 1 million, then I say that now that star is 2 million years old. Okay, now there is this problem of simultaneity. So if we are, question? Which both? Well, you see, well, let's forget the death. Let's stick with the clocks. Which clock goes first? It depends depending on the observer. The answer is not a unique answer. If the observer on Earth has, if we are talking about the observer on Earth, he will see his own watch, his own alarm to go off before the watch on the ship. By see, what I mean is that I'm not talking about the time the light ray takes to reach from the spaceship to him. So he just looks at the watch. He looks when that alarm clock goes off. He calculates how much it took the light ray to go from here to here, from here to here, to him. And then he subtracts those effects, and then he can determine how much later the second clock went off, how much later than his own clock. Then there's the other observer on the ship. He will observe, he will claim that the clock he has went off before the clock on Earth. And they will be both correct. Basically because the time will change from observer to observer. Essentially here we are talking about two events. One event is that the alarm on Earth going off. The other event is the alarm on the spaceship going off. So we have these two events, two different positions and two different times. Their chronological order will depend on the observer. For some observer, clock A might go, alarm A goes off first, alarm B goes second. For another observer, it's just the other way around. But then there's a problem. There's another problem we have. So if the order of events changes, let's say that I throw this chocolate on this black chalk, it falls down. So I have two events. Is it possible that for some other observer, the chalk will fall first and then I will throw it up? We already said that the order of the events might change. Well, this doesn't happen. Not all the order of all events we can exchange. If an event A can cause an event B, their ordering is absolute. My throwing the chalk is what is causing the chalk to fall on the ground. So for every observer, my throwing the chalk will be before the chalk falling on the ground, for every observer. But if two events cannot cause one another, then their ordering will change. Cannot cause meaning that, maybe let me put it in a different way. If you send light from one event to the other event, if the light cannot reach the other event, then their ordering will be different. Yes, question?
When there is a third observer, according to the third observer, the guy on Earth is not moving and the other guy is just accelerating, or not accelerating. This guy, according to this guy, which clock?
Well, you see, well, when we are talking about observers, we are actually talking about reference frames. Yeah. So if there is a third reference frame which is moving at rest on Earth, well, it is more or less exactly the same as the reference frame of this guy. It's just the origin is shifted. So whatever this guy concludes, he will also agree. But there is another alternative. There is another, let's say, scenario. Let's say this moves with a speed v. There is a third observer moving with the speed v. V over 2, half the speed.
Yeah.
According to this third observer, both of these will be moving with the same speeds in opposite directions. This third observer will claim that both alarm clocks, both alarms went off at the same time. No, it doesn't. You see, if that is the case, then we cannot say that they will be going off exactly 20 minutes later. Then you have to somehow make an arrangement that when the first alarm goes off, it should send some signal to the second alarm to go off. But that means in none of the reference frames they will be going off at the same time. Okay, so see you tomorrow. Not tomorrow, on Monday. See you in the next lecture.